Okay, so this is basically repetition of what we've done so far. So we did a lot of equations, and we got this equations with matrices. Then we introduced this transformation, u equals y. What we'll make note of here is that the time derivative of this vector is y itself. So if you try to insert this vector into this, we just get the y 2 times differentiated back. Then with the c, get it back. But if we insert it here, see that we get k times y, okay? Or we also get k times k inverse, which is I, such that we are left with some extra g's and v's, which subtract, and they disappear. So that's why that first trick worked. Okay, next we introduced some minor transformations. So you see, in essence, this is the same, this equation down here is the same as the one up here. In essence, it's only some slight scaling. So M is suddenly called A1. C certainly has this CS times Young's modulus times A hat in front of it. And this K is certainly A2, and also the driving force, the vector driving force is also scaled, and some different time dilation there. Okay, so that's fairly understandable. We should be able to do this. Okay. Next, I said that both this A1 and A2 are so-called positive definite matrices, meaning that we can solve the generalized eigenvalue equation as this. Okay, so we can find all of these eigenvalues, lambda, and we can also find the corresponding eigenvectors. And using the eigenvectors, we can construct a matrix capital lambda such that capital lambda transpose times A times capital lambda, or A1, gives the identity matrix I, whereas for A2, we get this P, which is a diagonal matrix with all of the generalized eigenvalues along, well, diagonal. Okay? And you've done, I suppose you've done stuff like this before with the eigenvalue composition, but this is a generalized version. So this is not the same as the standard eigenvalue problem, which doesn't have this matrix here. So you recognize that? If I remove A2? Yep. So this is, you also do some kind of transform here. You're doing something with your space or your eigenvalues. Okay, so then I will introduce a new transform. I'll say that y equals lambda x. Oh, where are I? Yeah, there we go. This equals lambda x. Okay, so this should be possible to do since I already know lambda. I assume I found it. Well, math to find it, basically. Okay, so next I'm going to insert this into the equation here. We get then we should end up with, style this a bit, with A1 lambda x 2 times differentiated plus s over e a c lambda x plus a 2 lambda, this would be a dot, x equals h over e a f tau. Okay, that didn't really do much, did it? No? under C. Ah, yes, it's supposed to be A hat. That was the geometric mean of the cross section in our Perl string. Okay, so this didn't really do much, just more complicated equation. But if I now multiply with the transpose of this capital lambda on the left-hand side, such that I get lambda t a1 lambda plus s a. So this is just a scalar. So I can this lambda t d plus lambda post a2 lambda x h over e a oops lambda t f of 4. Then we can, because the way these lambdas are constructed, this is just identity vector. First thing here. Now we get x plus over e a lambda dot plus diagonal matrix x h over e a hat of 4. Okay, so there's still some coupling going on here. But so it looks easier, but the problem is it's still coupled in C. But if we look at real-world examples, it found that C, or this C matrix, is often times A1, just empirical. That is to say, they've done some experiments, and they found this to be true. So this here is just a constant, scaling constant. Okay, so that's all well and good. So if I insert this T matrix into here, well, the CD we can just take outside, no? And then we're left with lambda T, A1, lambda, and that should be equal to the identity matrix. No? I'm going to introduce, say that CD zero robot zeta 0 over A 0 is called OK approximation. Again, empirical. And we already have all of the zetas, and we already have this A. So that's this is the cross section of the first block moving up and down. So our next stop is going to be double dot data over n. So this is just a number dot plus the diagonal there equals h e a at m dot t f all, where this one, and repeat it, is supposed to be 2 pi the length, the drill string this time, u bit of sound in steel, not the game, e 1 a times 1 plus alpha I squared over minus alpha I squared logarithm 1 over alpha 1 minus 1. And then coupled. Let's say, is x1 coupled with x2 in this equation? So these x's here, that's just, well, those are just x's. So the x0 here equals some kind of scaling of this. So that's just a number. Again, just x1. This is a diagonal matrix. So again, just x0 and then equals some kind of function here. Then now, through some cool math, and eigenvalues and transformations, and some engineering stuff, well, empirical testing, basically, we see that we can actually decouple these equations. So finally, we can do something with it. Well, actually, we're going to do some more transforms to tidy it up. But yes, and this is a project in itself. More transforms. So I'm going to say that this tau over there is a new tau tilde times the amount of oscillators I have, and then we'll let omega I n the I eigenvalue and psi I the omega I, and also 1 I. This is the first element, the ith vector. And then we get a second order differential equation. Then we get I double dot plus I plus the I squared I and A1 I T. So this is second order differential equation. And we've done this before, haven't we? We've solved second order differential equations. So this one has both a homogeneous solution and a particular solution. So the solution equals, well, homogeneous plus so what's the homogeneous solution of this? We basically set the right-hand side equal to 0, and we can solve this partial differential, and then we can solve this second order partial differential equations in normal ways. But it's homogeneous because whatever that is, it's just going to add up to 0. We also need a particular. The first, the homogeneous. That is to say, this Q tilde equals 0. That's how you find a homogeneous solution. Okay, then I will posit that xi of tau equals a I exponential function I tau tilde sine of squared 1 minus I squared omega I tau tilde plus I. I'll go through all of these later. Or basically a I x over 2 tau tilde times sine of omega I tau tilde plus I or x sine I 1 and omega d I is square root of minus a squared I. This is the damped is damped frequency. Gold. Okay, so what are we missing here? We're missing the AIs and BIs. Those are from initial conditions. So AI is going to be the amplitude of the oscillations. So if you push really hard, AI is going to be larger. If you push soft, AI is going to be lower. And this B, that's basically the phase. That depends on if you start at time 0, push, then I guess BI is going to be 0. But if you wait and then push, then BI is going to be something else. It's just a phase term. Not just, but it is the phase term. So if you try to ignore all of these weird symbols, you see we have an amplitude, an exponential function with something in it, dependent on some time tau tilde times sine of some kind of stuff times tau tilde and plus a phase term. So have you seen these kind of damped oscillators before? Should have. So let's see if we can actually show one. So depending on how you actually dampen this system, so that is depending on these stuff inside here, you can get oscillations that go, so they die out, or you could critically damp it, or it could also explode. So if it's not dampened enough and you just push and push and push, you will get an oscillation. So just start here and just explode. That's just the homogeneous solution though. So this is actually when you don't have any force. So what you can have here, so if you first have some kind of force and then you stop, then this is how it will. So what we've done here, so we've applied some kind of force, okay? We haven't looked at the particular term yet. We are going to soon. But if you have first set it in motion and then you stop pushing the system, then this is two of the responses. If it's also critically damped, it could just continue going all the time. But then that means you also have no friction forces. You do. And also this is unrealistic. If you stop applying energy, it's going to stop, no? To reiterate that last part, something like this is going to be a response of just one element after you stop pushing it. This isn't physical, just mathematically possible to happen. Okay, the particular solution, though, is more difficult to find. So the general thing you do here is you do a guess, and then you see if this works. If it doesn't work, you try to guess again. So that's what we're going to do. We're going to try to make a guess, and then fit it to the equations such that it works. So I'm going to try to do this in a better fashion, but we're going to rewrite this second order system into two first order equations. So that means we can use so-called integrating parts to solve them. So I'm introducing, I only use, okay, yeah. So I'm going to go back to y, get it, I, y. Yes, this is a very particular solution. Could have said it, but in steps. Oh, of course. I'm introducing a new vector y, I. It's not the same as the one earlier, plus the I of tall. So this is my guess. This is just my guess. And then we have that y I is a vector with x I tau tilde and x I tau. B I going to be 0, 1 omega I squared. This is a 4x4 matrix, and bi tau tilde 0 is a 1 lambda 1 I q tau tilde. So that's same equation. It's only written as first order differential equations instead of a 1 second order differential equation. Okay. So this is just a rewrite of the same equation. So what I'm going to do now, I'm going to guess a particular solution. X first. That's basically what I've done here. Step 2. Guess a solution. So my guess is going to be educated, and it's going to be that y I, and I'm going to use p for particular solution. This is going to be the differential function times tau bi z I vector. Okay, and then come back to what z is. So that's my guess. Okay, then we have to see if this actually works. So with that guess, I try to differentiate it in time. My p equals differential function tau tilde bi set I, yes, or tilde. Well, it's an exponential function, so this keeps happening. Times tau I z time. And we can try to rewrite this, actually using my guess. And we will end up with b. So you see this down here, basically this equation times I p exponential function for I percent of tau. Okay, so that's my guess. Next, we have to see if they actually. Okay, so trying to insert this, we get that exponential function of tau bi percent of tau I tau. Then we can figure out what this Zi is supposed to be by so change it in time. So Zi of tau is going to be, well, integrate from 0 to tau tilde. Exponential function minus bi I of u, because I'm just inserting. So this u here is just a placeholder for tau when I'm doing the integration. Ci, we are soon there. We're soon there. Okay, so let's see. Solving or integrating this, running out of time, so we have to do some skips. The IMP. Of U bi U bi bi. I can mention that this Ci, this is a constant we just introduced. We can find this from the initial conditions. And this bit here can be found by using, let's see, okay, so this bit here, we can rewrite it. I'm going to introduce some fancy matrices. This functions of tau I will tell you what these are later times identity matrix plus I 1 for I, where that's 0 to have to use my note details to expression cosine omega di. So this one we have. If you want to work more on this, just to take a look at the note for some of the details I'm skipping now. And this is what's called engineering math. It's complicated. It doesn't look nice at all. But this will be implemented on the next exercise. Then you should have gotten code that solves these equations. So I suggest that you at least play around with the code. Tau over this, oh my god, driving angular frequency. And this, mention it, this is called the Cayley-Hamilton Theorem. So I have to admit, I don't know the details of this Cayley-Hamilton theorem, but this is what you get. What I'm going to do then, 5 more minutes, is yes. I guess I'm going to give you the full solution to it as I'm going to skip some details. I guess this is already too detailed, so yes. Going to be the full solution, also the last thing we do today. Eigenvectors in front of them. And actually solving this, you need to integrate it. Minus u 1 times the driving force. And then plus homogeneous term. Okay. Tau plus the base term. I think. Okay, so the message to take home here. Start with a very simple system, just harmonic oscillators, and we are trying to solve it. And if you actually try to express this, transform it back, so you have to solve this, and then you have to take the solution, and you have to work backwards to actually get to the displacement from equilibrium for each harmonic oscillator. And you can study how the drill string will behave when you apply this and this force on it. So you can actually analyze this, and then you can see how I most efficiently drill through this rock or control the drill string such that something doesn't break. So what you want to do here is to actually avoid resonant frequencies. That's one of the main points here. So by looking at this, studying it, the thing is you can maybe do something more analytically, but this almost has to be done numerically if you want to test a lot of cases. For testing this, you can look at different frequencies and see if some of the frequencies driving a drill string will actually break the drill string. Because breaking the drill string when it's down in the borehole, that's expensive. Then you're not going to get it up again. And you have basically ruined a perfectly good hole, or borehole, anyway. Yes. That's a lot of math. Next time we'll have the finite element method, which is a more general way of solving finite. Oh well, it's more general than finite difference methods. Anyway, so you can have a different sized grid in different areas. In order to do this, we need to introduce some more transformations and the so-called basis function. It's also going to be a lot of math, but fun. I think it's more fun than this. Well, the beginning is fun, but the end, when you get with these area equations, don't like it. Or for making you suffer.